Okay, so our last lecture series for carbonyl reactions, but our last lecture series for the course as well. And this is going to concern type 3 carbonyls. So what is really type 3 carbonyls? Okay, so we've talked about type 1 carbonyls, and these were things with very good leaving groups. These were things that basically carbon could kick off and reform that double bond with the oxygen. The type 2 carbonyls were basically carbonyl compounds that could not kick a group off, and it could not form that double bond with the oxygen again. So oxygen was kind of stuck. It had to basically take that cleavage of the double bond and fix it itself. And traditionally, this came in the form of some type of hydrogen that we could sandwich on top of that oxygen to take care of that negative charge. Now we see type 3 carbonyl. And a type 3 carbonyl, you're probably wondering, well, how many more functional groups could there be? I mean, we've just spent over 60 videos really talking about functional groups and naming them and reactions with them. You're telling me that there are more? And the answer is no, not really. They're not more. But the type 3 carbonyls, well, it's going to refer to other reactions that we might not expect based on our lecture series beforehand. And these reactions are going to focus on something that we call the alpha hydrogen. What is the alpha hydrogen? What's the purpose of the alpha hydrogen? What does the alpha hydrogen do? That is the question that we need to answer before we really understand how these reactions begin to go forward. So for instance, let's say that we have a molecule, and let's pretend that this molecule is a carbonyl. So we have a C double bond O. On this side, I'm just going to put R for a random alkyl group. On this side, I'm going to put CH2 here, and then we'll put an alkyl group there. So it can be anything else that it wants to be. So with the Greek nomenclature, this is not surprising, right? This is my carbonyl bond, and if I wanted to number the longest carbon chain, then, this may be number 1, and this is number 2 carbon, right? Well, the same kind of thing can happen with the Greek letters. There's no difference, there's no changes. This was the carbonyl bond, and that means the one directly beside of that was called the alpha carbon. And then if there were any others, we called that beta and gamma and delta and so forth. So you get the picture. Nothing's really changed, nothing new. Well, these reactions are going to focus on the alpha hydrogens, which means that these are hydrogens attached to the alpha carbon. And our alpha carbon is right here. So in this setup, we have 2 alpha hydrogens, right? Because that carbon has 2 hydrogens attached to it. So there's something very special about this hydrogen. So let's redraw this structure a little differently. Let's put R, CH with the hydrogen kind of being pointed down, carbon, double bond O, and then whatever random alkyl group wants to be on that side. Okay, so here's the thing with the alpha hydrogens. This is why they're so important. This is why maybe we didn't expect it or see it coming from before, but now we do once we get this description of what goes on. The alpha hydrogen is something that we call acidic. Acidic basically means it can be donated quite well. The molecule can look at this hydrogen and say, nope, you got to hit the curve, you got to get out and you got to work for a living. I'm tired of you mooching off of me. And that's what the molecule does with the alpha hydrogen, right? It kicks it out. It puts it out into the real world. And it wants it to go do its own job. And if it can do that, then it can free up that carbon's life. It's like that kid that never wants to leave home. If you can kick that kid out on the street and let him work for a living, then it makes your job a little bit easier, hopefully, at home, because that's one less person that you've got to worry about. Well, if this molecule can kick the hydrogen off, okay, if it can take this hydrogen and get rid of it, bye-bye hydrogen, go to college. Well, that hydrogen leaves behind its electrons. In the bonding, it leaves behind the electrons. So those electron pairs stay behind, and this carbon now becomes negative because it has one less bond that it had before. Formal charge makes that a -1. Well, look at the beauty of just what happened. Everything at home runs much smoother now. The hydrogen's off, no longer bumming mom and dad for money. That carbon's taken those electrons from the hydrogen. It's taken that extra cash that it's saving, hopefully, and now it can distribute it to the remaining family members. Because lo and behold, what has happened here is that we have now formed delocalization. This negative is now on this carbon, and that is neighboring a carbon that has a double bond on it. So now this molecule can delocalize. And that is wonderful news for the molecule because it likes when this happens. So now we get this negative charge on the carbon that can basically be smeared throughout this entire area of the molecule itself. That oxygen's electronegative. It can pull the electrons up through it. We can see this electron movement throughout the molecule, and now all of a sudden we get a pretty stable molecule based on delocalization. So this is the reason why the hydrogens on alpha carbons can easily be removed. And that will be a test question. I'm just going to go ahead and tell you now. One of these things, test question wise, would be, why are the hydrogens easily removed? Why are they easily removed from the alpha carbons? And now you can kind of explain why that happens. Because once they go away, they leave behind their electrons, and the carbon can take those electrons and distribute it through the carbonyl bond. And we get some delocalization that happens. And delocalization is good. It's good for me, it's good for you, it's good for everybody. So this is the story with the alpha carbon. This is the story with the alpha hydrogens, and this basically is going to lead in to some reactions that we might not see or might not predict before this lecture series has arrived. Now, the other question that we have is, what can remove the hydrogen? Okay, the hydrogen just can't be kicked off on its own, right? The hydrogen's going to stay around until you force it out of the house. So this child of hydrogen is going to continue to live at home and mooch off of you and all of the hard work that you do when you come through that front door until you look at it with love and say, hydrogen, I love you, but you know what? You've got to go bye-bye. You've got to grow up. You've got to make a life on your own. And we've got somebody here that can help you out with that. So why don't you go along with this person? Why don't you go and start your own life with your buddy or whoever you want to bring into the picture, and leave us alone for a while. It's time for you to grow up. So we need something to help provoke that hydrogen to leave. We need it to come out of the front door, get in the car with its luggage, and go bye-bye. And what we can incorporate here is a base. We need some type of base in order to remove the acidic proton. That makes sense, right? Acid and a base react together. So the base is typically represented as a B with a negative charge. You know, you can almost think of this like a nucleophile in a way. This nucleophile is negative, and it can come into the picture and it can pull a hydrogen off of the acidic carbon. Okay, so now we have an issue. Now we have a nucleophile reacting with a carbonyl to give us a product. But we also have a nucleophile that maybe could react with the acidic alpha hydrogen and pull that hydrogen off and get a different type of product. So we're going to have to kind of go through this step by step, look at these reactions, and just understand for a minute that both routes could possibly happen. And we've talked about one route already, and we're getting ready to talk about the second route now. Just some terminology issues that I want to talk about before we go to the next video, and that's this carbon with the alpha hydrogen. We call that the alpha carbon, of course. But sometimes we also call this the carbon acid. So that is another term that it can go by. So don't let that throw you off. So carbon acid is basically representing this carbon is acidic. And this carbon can give off a proton if it needs to. So it's all based on delocalization here. That's what this thing is all about. It's delocalization driven. Once that hydrogen goes away, we get some electrons that can be scattered and spread throughout the entire molecule. So in the next video, we'll continue this discussion with type 3 carbonyls, and we'll continue on and we'll look at some initial reactions that we can do with them.